The title of this presentation is Modified Pulse Reservoir Routing in Excel with one click. This is part of the training seminar organized within the DRIP project in India, where DRIP stands for Dam Rehabilitation and Improvement Project. This project is funded jointly by the World Bank and the federal government of India. What we see here is the classical routing equation written in the units of volume for both sides of the equation, where the average inflow is multiplied by the length of the time step, and the average outflow over a time step is also multiplied by the length of the time step. And the difference between average inflow and average outflow equals the storage change over a time step, where the index I represents the storage at the beginning of the time step, and index I plus 1 represents the storage at the end of the time step. This is a mass balance equation. To solve it, we also need additional relationship between elevation and storage and elevation and outflow. These two functions are interconnected because for one elevation there is a unique value for storage and also a unique value for outflow. The modified pulse calculation method has its assumptions. Number one assumption is that all coordinates of the inflow hydrograph are known. Also, the functions relating storage to elevation and elevation to outflow are also known. And finally, the initial storage or the initial elevation is also known. You will notice from the previous equation that it has been rearranged here to move all known components of the mass balance equation on the left-hand side. As mentioned earlier, all inflow hydrographs are known, so we can calculate the average inflow for any time step. The initial elevation is also known, and the initial outflow that corresponds to this elevation is known. So all constituents on the left-hand side of it can be calculated for the very first time step. The trick of the algorithm is to split the value of the left-hand side, which is equal to the value of the right-hand side, into the ending storage and the ending outflow at the end of the time step, which will then become the starting storage and the starting outflow for the next time step. So this is an iterative equation where the term on the right-hand side moves to the left-hand side for the next time step with a minus sign for the constituent that depends on the outflow. And this is going to become clear from the numerical example. We're going to look at the numerical example in terms of using the polynomial fit to represent a functional dependence between the variables, as well as linear interpolation. The first presentation will be using the polynomial fit because it's easier to understand the algorithm without going into the details of an otherwise complicated linear interpolation formula. So let's begin. Let's move on to the spreadsheet here. You can copy the header of the spreadsheet to contain the following entries. What you see in the first column are the time step lengths in hours. In this particular case, we have time step which is 1 hour, so the difference between 1 and 0 is 1, the difference between 2 and 1 is 1 again, and so forth. We could have done a 2-hourly routing or a 3-hourly routing or 4-hourly routing. In this case it's 1 hour, but if it was a 2-hour routing, we would have 0, 2, 4, 6, 8 and so forth. The next column are the ordinates of the inflow hydrograph. You see this column shaded in gray. We are going to leave it shaded in gray, along with these columns on the right-hand side of the spreadsheet, which are also shaded in gray. This is the input data we have to prepare before being able to do flood routing for any dam. Eventually you will realize that once the spreadsheet is set up, all you need to do is copy data from another dam prepared in the same way, and the spreadsheet will work for any dam. So the first thing we have to do now is develop this composite storage outflow function, and we'll place it in this column here. This column is equal to storage in the same units, millions of cubic meters, plus half of the outflow, so outflow divided by 2, and then multiplied by the length of the time step. The length of the time step is 1 hour, so you can simply put 3600 seconds, but to be more general, we should introduce this incremental difference between the ending coordinates for each time step, and then multiply that with 3600 for every hour, because the length of the time step can this way be possibly longer than an hour, and divide by 1 million to convert the cubic meters into millions of cubic meters. So this is the first value, which corresponds to the initial conditions here, and then we can just copy and paste this to all other pairs of elevation, outflow and storage points. Now we need to develop a relationship. That will be our first relationship. So let's do a polynomial fit. We are going to create a plot by using insert and clicking on a plot graph that looks like this. Let's bring this down a little bit. To make this more visible, we can start the plot from 300 here. You can right click on the points and click on the add trend line option. We can click on the polynomial option here and select polynomial of the order 2, which is good enough for this case. And what we need is the equation and the r square of the fit. Now this equation is not given in sufficient number of decimal places here for us. We want to have higher accuracy, so we're going to format trend line label by introducing more points, let's say 9 for example, or maybe even more. In general, there is no harm in introducing additional points. So this will be one relationship we're going to use, and we'll call this elevation versus storage plus Q delta T divided by 2. The other relationship we're going to need is the relationship between elevation and outflow. So let's do another quick insert, scatter point, and we're going to place it next to this function, and we're going to call it outflow versus elevation. Now this function can be fitted by a second order polynomial, and if you see some discrepancy between individual points and the curve, you can even select a higher order polynomial. The best way to check the fit is by again looking at the r squared and r squared or the functional fit. So again, format trend line label number, let's take 12 decimal places, and see this fit is almost 1. We have 0.999987 if we change this fit to the second order polynomial, it's going to be 0.99925. So the third order polynomial is a better fit. So now we have functional dependencies that we're going to use later. Let's go and build a spreadsheet from the second column forward. The first thing we'll be doing, of course, is calculating the average inflow. We have inflow at the beginning and inflow at the end of the time step. So the average inflow per time step would be, you can use the average function in Excel, average of these two. And then we want to convert this average inflow to millions of cubic meters. So this is going to be flow times the time step length. Again, to make it more general, we will calculate the length of the time step as the difference between the time coordinates, times 3600 and divided by 1 million. 1, 2, 3. Next thing we're going to need here is the very starting value of this composite storage outflow function. In our particular case, that value is going to be this value. So we can either copy this as a link, or we can copy it as a fixed value, because sometimes we may pick any other value from this range. Let's copy it as a value for the moment. And then the ending storage, essentially for the very first time step, is de facto the starting storage. And we can do the same thing here. We can take the starting storage that corresponds to the initial condition and plug it in here. Now, the interesting thing is that we can now use our functional dependence to determine the elevation and outflow. So the elevation is going to be defined as a function of this composite storage and outflow. Let's copy this formula. So here's the formula. We need to put the equal sign here, and we need to use the argument in the function and square the argument instead of observe that this functional fit is actually pretty good. We're getting 744 meters, 0.0036, while the actual starting elevation is exactly 744 meters, as you can see from the input data. It's a very good fit. We don't always have such good fits. The next thing we're going to do is determine the outflow based on the starting storage. So there is starting, outflow, and then this is why we created this function. Again, we're going to copy the formula and paste it here. Now our argument is the elevation, so that is cell H2, which is going to the third power here, times H2 to the second power, and then times H2 here. And here we can see that the reading isn't quite the same. We have 869.93, and here we have 869.383. Now we'll see how much that affects the final results. The next thing we can calculate is this term in column E. So we're looking at cell E3. This will be calculated by using both the outflow and the composite storage. And the formula is going to be the composite storage, the initial composite storage, minus the entire outflow, because here we're looking at composite storage plus outflow times delta T divided by 2, and what we need is the composite storage minus outflow delta T divided by 2. So if we subtract the entire outflow, not just the half, then we're going to have the desired result. Again, we have to convert this to the units of volume. So we need the time step length times 3,600 seconds in 1 hour, and then divided by 1 million. So this is the first value that resolves the left hand side of this equation. That left hand side is equal to the right hand side for the end of the time step. So we're simply going to sum up the average inflow plus the left hand side, and now we are getting the composite storage plus half of the outflow at the end of this time step converted to units of volume. Now that we have the updated value for the composite storage outflow function, we can retrace the steps that we did in the beginning. In other words, we can read the new updated elevation, which is now going to be a function of composite storage outflow function at the end of the time step. And once we have the elevation, we can also update the outflow at the end of this time step. When we have the outflow, we can calculate the ending storage. Now that we have the composite storage function at the end of the time step and the outflow at the end of the time step, what we need to do is we need to take half of the outflow at the end of the time step and subtract it such that we can get rid of this second term in this particular expression. So here we go. Composite storage minus outflow divided by 2 converted to the units of volume times 3,600 seconds divided by 1 million. And finally, there is something else we should do just to make sure that our calculation is correct. There is another way to check the mass balance equation, which is a standard way of summing up the starting storage, which is the ending storage from the previous time step, plus the average inflow in the units of volume, minus the ending storage for this time step, minus the average converted to the units of volume. We need to make sure that the mass balance works. So we have now completed the calculation for one time step, and in order to complete the flood routing for the entire flood hydrograph, all we need to do is copy and paste this for all other ordinates of the hydrograph. Here is our result. From this, we're going to read the maximum elevation reached during the simulation and maximum outflow, and you can see them here in the highlighted cells. Now, the same calculation is done in the next spreadsheet, where you can see a copied image of this spreadsheet. One important difference: instead of using the polynomial fit, we're using a complicated linear interpolation formula. Here is the formula. It fits on 3 lines in the spreadsheet, And what it does is it takes as the argument the value in cell F2, and then it searches through the values of these two columns L and M. The column length stretches to 100th row, so we can have up to 100 values. Usually this is not necessary. We only have 7 values that form these curves. But it finds the appropriate segment where to conduct linear interpolation. And as you may remember, linear interpolation is de facto a triangulation within the appropriate segment based on this formula, and this is the solution for the unknown given the known input and the known arrays of x and y. This formula is given right here, and it'll be given in the spreadsheet for which the downloadable link will be provided. But at this point, it's important to note that instead of reading from the polynomial fits, we are using this complicated formula which does two things. It finds the right segment where to conduct interpolation, and then it conducts the interpolation properly. This particular instance, we have input of 308.986, and we are reading the value for elevation. So let's check if this really works using some other formula that you may be familiar in the spreadsheet. For example, we can use the trend formula for 308. We're going to be in the very first segment here, and we can just calculate the interpolated value directly for this segment using the trend formula. And we're getting 744.107, and in this particular case it is 744.107. So this formula, even though it looks cumbersome, it uses the match and index commands, and you can read about them in Excel manuals and online. Is a very powerful formula that does both the search and linear interpolation calculation, and it's used to convert the composite storage into elevation, and then it's also used to convert elevation into flow. So remember, the first time around we had a slight difference in reading of the outflow. In the previous worksheet it was 869.93 instead of 869.38. Well, the linear interpolation formula does the accurate reading, so we're never going to have any differences. This is very useful when we have instances where the interpolation with polynomials doesn't work very well, because not all the functions can be represented by a polynomial fit. Now let's look at the differences in the final results. Here our maximum elevation and maximum outflow are 745.9, and maximum outflow is 1613.3. In the previous polynomial interpretation we had 745.918, so we are off by 1.8 centimeters, and we had 1614.31, so we are only 1 cubic meters per second different. In fact, let's just see what we get if we do this. 745.904 is the maximum level versus 745.918, so we're looking at 1.4 centimeters. If you want an accurate solution, and the question is really which one is more accurate. Mother Nature is not linear, we know that, but then again, if we don't have any values between the 2 points, do we use a quadratic or a cubic function, or do we use linear function? It really depends. Either one is theoretically okay. Typically, if you have more points, a linear approximation is practiced more frequently. Let's now examine one more thing. I'm going to show you an example of another dam where we have to start typically with outflows that correspond to the outflow capacity at the full supply level. So in this particular case, the outflow capacity at the full supply level is, on the inflow hydrograph, is this value. So if we do the routing by assuming that the initial flow is going to be equal to the maximum outflow capacity, then we will have no possibility to do any pre-flood drawdown. And you can see what happens here by looking at the maximum water level and maximum outflow that was reached. So we're reaching 404 meters, 404.554 meters, and the maximum outflow of 21,447 cubic meters per second. This was the starting storage. This was the starting elevation. This is the full supply level, or full reservoir level, FRL as it is called here. The corresponding storage and the composite storage function are entered as the initial values here. If we wanted to see what would have happened if we had 1.5 days or 36 hours of flood forecasts, then we would take this inflow hydrograph that starts 36 hours earlier, because you can see after 36 hours we reach this initial flow that we were using earlier on the hydrograph. This is now the entire hydrograph. We can copy this hydrograph here as values. This is all going to automatically update the spreadsheet. We have the same starting level, but we now have time to react. So you can see that the reservoir elevation is first dropping because the outflow is higher than the inflow, and eventually the reservoir begins to fill. Now we can't quite see the result here. We can't see the maximum because it didn't happen yet, but we can just simply copy and paste this further down and complete our calculation and compare the maximum now. The maximum seems to be right here. So instead of 404.55, we have 403.867, roughly 70 centimeters lower level. The flow has only dropped by about 1,000 compared to what we had before, but the important critical elevation has been lowered by 0.7 meters. So this shows the importance of having flood warning systems and having foreknowledge that the flood is coming at least 36 hours ahead. This also shows that anytime you want to use this kind of calculation, all you need to do is make sure that you have these three columns placed here. They have to all be in ascending order, and the points have to correspond to the points read from the elevation outflow curve and the elevation storage curve. This, of course, is recalculated as we've explained already, and now we can change the starting elevation by picking any other starting level, and for that level we're picking storage and the composite outflow function and putting them here. Also, we can change the hydrograph by copying and pasting a different hydrograph. Here's how this works. It's pretty simple and straightforward, and there is no need for any manual calculations once you set it up. That was all. Thank you very much for your attention.